So chapter 9.1 introduced us to roots and radicals, and 9.2 is going to take our understanding a little bit further, and we're going to be simplifying radical expressions. So all of the stuff that we were talking about still holds. Hopefully that classification of values is something that you can remember when you start the next level course. And really what we're going to deal with in these is simplifying things that have square roots in them. So to reduce a fraction, we know that was its simplest form. We would look for things both being divisible by a certain number. So if we have 4 over 6, we know that we could reduce that as 2 over 3. And generally, we want our answers in simplest form. We also reduced rational expressions back in chapter 5, right, where we simplified those rational expressions. I got to write it out because there's too many R words. So this is really the third time that we've been simplifying things. Maybe more when we were collecting like terms or all the exponent rules. So this is a common thread through the course. And when we're talking about square roots or radical expressions, there's 3 key things that are faux pas. There's 3 key things that are not allowed. If these things exist, then your radical expression is not in simplest form or in lowest terms, if you will. So the first thing that we look for is that there are no perfect squares under a radical sign. And so as an example, if we have the square root of 4 over 2, that is not in lowest term because we have a perfect square under a radical sign. And so my answer for this would be 2 over 2 or 1. The other thing that we'd look for is that there's no fraction under the radical sign. And so we've been seeing things like this before, and we've actually already done this. So if we had the square root of 4 over 9, we said we could break that apart as the square root of 4 and the square root of 9. So that's something we've already seen as we went through that 9.1. The third bit here is that no radical sign can appear in the denominator of a fraction. And so the example for this one that we're going to learn how to rationalize the denominator would be an example of, let's say, the square root of 4 over 3. So in this one, we can break it apart, which was the second criteria here, the square root of 4 over the square root of 3. And we can take the square root of 4 as 2, but we can't take the square root of 3 and get a rational answer. We'd get a weird number. We'd get an irrational answer. And so we're going to learn how we go beyond here to satisfy that last criteria. And satisfying that last criteria is the last part of 9.2, where we rationalize the denominator. So just a quick recap of what we were dealing with. One thing that is a valuable tool is, and I'm going to switch colors for this, the list of awesomeness. The list of awesomeness is key because it's the very first thing that we have to deal with when we're simplifying radical expressions. And so in these ones, we got a few examples here. We're going to start with that first criteria as we go through. So if we have the square root of 17, we can't make that any better. There's no factors of 17 that are perfect squares. If I compare that to the square root of 12, square root of 12 is not in simplest form because I could break it down into square root of 4 and the square root of 3. The way I write this down would be the square root of 4 and the square root of 3. So these are equivalent expressions. This one and this one, they have the same value. I've put this awesome thing out the front because I can now take the square root of that to get 2 root 3. So here we'd have the coefficient of 2, the radical sign with the index of 2, understood, and my radicand underneath. So that would be square root of 12 simplified. We're going to do lots of these. That's just the first example here. You can go back and forth. So the idea here is that if you have a complex number, say like 36, you can break it up in, I'm going to pick a different number because I don't know if that one's the best one. We can break it up into any combination of factors that we find to be useful. So if we have the square root of, I'm going to go backwards here. Hang on. Let's pick an easier one. So let's go the square root of 32. So I could break that up into the square root of 16 and the square root of 2. Those are equivalent values, but then I could take it one step further to say it's 4 root 2. So this is more like what we're going to be doing in this chapter. This is one that you could do on your calculator to buy into. It doesn't matter how you get there, the answer is the same. So it's basically, this is the rule. It's kind of like an exponent rule, if you will, to kind of guide our thinking here. It does specify for any non-negative real numbers, A and B, so all those things that would give you an imaginary number. This is going to hold true. So let's try these ones. So what we're doing is looking at these numbers suspiciously under the radical sign. If I have 45 under the radical sign, I might want to look at my list of awesomeness. And so I'm going to take a minute. So we could take the square root of 1 and get 1, the square root of 4 and get 2, the square root of 9 and get 3, square root of 16 and get 4. This is why it's handy to have it written on something else, like that. I'll keep going. What am I at? 49 is 7. Square root of 64 is 8. Square root of 81 is 9. And the square root of 100 is 10. Anything more, maybe we could use our calculator. So this is my list of awesome. So if any of these numbers are factors of numbers underneath the radical sign, we can break them up in a way to simplify these radical expressions. So this one, I can break it apart into 9 and 5. 9 is awesome because I can take the square root of that. I'm going to switch colors here because sometimes that's a tricky step for people. The square root of 9 is 3. And I can't take the square root of 5 because that is an irrational number. It's not nice and neat. So this has switched my radical expression into lowest form. I'll do a few more here. So D, I would look at 20 suspiciously and wonder if there's any factors of 20 that are in my list of awesomeness. If I take a look, I might want to work from the bottom up to get the biggest number. I could break this apart into square root of 4 and the square root of 5. This is awesome because I can take the square root of 4. The square root of 4 is 2. So, whoops, I didn't switch colors. So my answer would be 2 root 5. Let's do a few more of these ones. So G. G has me breaking it apart in any way that's convenient for me. You might want to take a look at your list of awesomeness and find a number that is a perfect square, and then test it out to see if we can divide 48 by that number. I found that you could divide it by 16 and 3. You want the biggest number possible out here. So in this one, we get 4 root 3. Give these ones a try. I'll throw the answers up and then I'll talk through them because sometimes people get this pretty quick and sometimes it takes a minute or two. So if I talk through these ones, how I got to them, 72, you might have got there different number or different ways. So I take a look at it and I look for the biggest number that would divide into 72 up my list of awesomeness here. I could break it apart into the square root of 36 and the square root of 2. That's how I got to 6 root 2. Now I just want to, I'll come back to that one. So this one, 75, I take a look at my list of awesomeness. I can see that I can divide it up into the square root of 25 and the square root of 2. I can take the square root of 25 to get my 5, and I leave the square root of 2 alone because it's not a nice, neat number. For F, I'll do them slightly out of order. I would take a look from the bottom up for numbers that would divide into 98 and use your calculator, check things out. I could break that up into root 49 and root 2. And taking the square root of 49 gives me my 7, and I leave the root 2 alone because there's nothing I can do to make that any better. For C, has a lot of things going on. So I have a 5 as a coefficient here. That just means that I'm going to multiply it by whatever this is in simplified form. So I've shown my work and that I could divide 18 up into 2 factors, that first one being awesome, being 9 because it's in that list of awesomeness or perfect squares. And then I could take the square root of 9 to get 3. My last step here is to multiply what I have now as 2 coefficients. So I get a final answer of 15 root 2. So if you're feeling good on that, that is awesome. If you remember how we simplified fractions, how you didn't have to get the biggest number right away, it's still possible to do with this one. So when you take a look at 72, you might instantly think, oh, 9 and 8, right? That would be equivalent expressions, and I can take the square root of 9 and leave it like that. And you might think, there, I'm done. But every time you should look back at what's underneath that radical sign and think, is there anything in this list of awesomeness that is a factor of that number? And here I could divide it up into root 4 and root 2. And then I can take the square root of 4, so I'd have 3 times 2 root 2, or 6 root 2, which is exactly the same answer as I got over here in one step. So sometimes it takes multiple steps, but you can take it little by little and get to that same answer. So it's kind of similar to simplifying fractions that way. We're going to move on from just the numbers that are radicals and simplify things that now have letters in them. You knew the letters were coming. So in these ones, we're going to deal with the coefficients in the same way. And as far as the exponents go, we can take the square root of a variable if it has an even number on that exponent. So we're going to still break these up in ways that are convenient to us. We're going to pull anything that's a perfect square out the front, and you might remember the even numbered exponents from our difference of squares back in chapter 4. We recognized perfect squares already. So we're going to break these up into factors, one of which hopefully is a perfect square that we can take the square root of, and then whatever is left behind is that irrational component. So in these ones, if I break them up, I could take anything out front that is a perfect square. I'll switch back to colors. So I could take it a root x squared out the front and a root 5. The root x squared is awesome because I can divide my exponent by my index and write it as x. So x root 5 would be that first expression fully simplified. Let me walk you through a few more here. So if I go down to b, I can break up x cubed into the square root of x squared and the square root of x. This out the front is the perfect square. That is the thing that is awesome that I can take the square root of. So simplifying this one step further, I take the square root of x squared and get x and write my irrational component out the back like that. For C, more coefficients and variables. So I could break this up. Anything that's a perfect square could go out the front, and I'll take as much as I can and rewrite it as an equivalent expression, leaving the leftovers hanging out the back. So now that I have the square root of 4b squared identified as a perfect square, I can take the square root of that and get 2b. I'd still leave that irrational component tacked on the back because I can't make that any simpler. Working through these, I'll just keep talking them through. I want to break up these numbers into perfect square and then whatever's left over. So I could break this up. I could pull a 9 and I could pull 4 A's out of that A to the 5. Everything that'd be left behind would be a 2 and an A. I should be able to reverse this and go back to my original question, but the key thing here is that I can take the square root of that thing that's identified out the front because it should be a perfect square. That's what we're trying to do, is make that thing really awesome out the front. So the square root of 9a to the 4th would be 3a squared. And then I don't want to lose the meaning of this or the value of this, so I tack that irrational component out the back there in my expression. E, I could break apart into the square root of 9x squared, and I'd have a leftover square root of x. And then taking the square root of that perfect square at the front gives me a 3x, and tacking that irrational component back on the end. All of these work in a similar manner. look at that list of awesomeness, pull out as many variables as you can, keeping an even number on that exponent. And then once you've identified that perfect square, take the square root of it to give your final answer. So we've got the second criteria to work through. So the second criteria says that we're not allowed to have fractions under a radical sign. So that second criteria, no fractions. That's okay. I'm okay with getting rid of fractions. So the idea with this is that you can break this up into root 9 over root 4. And we could simplify that as 3 over 2. This act of getting rid of the fraction and taking the square root of both top and bottom is what satisfies the second criteria of simplifying radical expressions. So for B, I could do this one. I could break it up as root 2 over root 25. Can't do much with root 2. I'm going to just leave it as an irrational numerator, but I can take the square root of 25 to give me root 2 over 5. I'm just going to work through these ones. We've got a couple more number ones, and then we'll go through the letter ones over on the side. So in this one, I could break it up so I can see numerator and denominator, and they're both perfect squares, so I can take the square root of them. For D, I break it up into root 7 and root 9. Can't take the square root of 9, but I can take the square root of 7, but I can take the square root of 9, so I get root 7 over 3. Moving on from just the numbers are the ones that are include variables. So in this one, we're going to break it up into two separate little questions. We're going to do what we can with simplifying this. So that numerator is actually going to employ the first criteria of simplifying radical expressions, in that we can break it up so we don't have any perfect squares under our radical sign. Oops, that should be a 2 in there. I don't know why I wrote an X. Get ahead of myself. So we'd have root 4x squared and root 2. And the bottom, we could actually take that. You could take that step now or later. So now we take the square root. Maybe I'll be consistent. I'll take it later. Doesn't really matter. So root 9. Taking the square roots, we get 2x squared root 2 all over 3. That's both rules together. Up to the top of the page, maybe I can fit all of these on at the same time. Same thing, we want to first break up the fractions, because that's no good, under the radical sign. And then we can see what we can do with both top and bottom. We want to employ the same rule that we were just developing with the first step of simplifying radical expressions, so we can break it up as is convenient to us. And then do that awesome step to take the square root. Oops, oh, I forgot that. A few more on the page here. Take your time in breaking up the fraction and then breaking down either the numerator or the denominator if you can. And then that act of taking the square root when you've found your perfect square, and like that. Last one, H. I'll show my work. So I'm going to break up the fraction. That's the second criteria of simplifying radical expressions. And then I go back to that first criteria. Anything that's under a radical sign, I don't want to leave it if there's a perfect square factor there. And so I would break up the top into 25x to the fourth and square root of 3. That's a 3. 3x. And on the bottom, still the square root of 4. So now taking the square root, we can take the square root of 25x to the fourth and get 5x squared. Can't do much with the 3x, so I leave it under the radical sign, and I can take the square root of 4. So the third criteria for simplifying radical expressions, the third criteria is no radical sign in denominator. It's considered poor form, if you will. So in order to get rid of that, we're going to practice this skill called rationalizing the denominator. And as a shortcut, what you really want to do is take whatever's in the denominator and multiply it by itself. Except for if we just did that, we would change the value of this thing. And so this is, I had an instructor once call it a very special one. We know that we can change the way fractions look by multiplying them or writing equivalent fractions. We're doing a similar thing here. Multiplying the top and the bottom by the same thing doesn't change the way or the value of this thing. It just changes the way it looks. And the key thing that we're trying to get rid of is we don't want a radical sign in the denominator. So basically, squaring a square root is like doing the reverse of something. So you take the square root of 2 and the square root of 2 and multiply them together, and that unlocks your radicand. It unlocks what's under the square root. Now, it makes a bit of a problem on the top here, but it's okay to have a radical on the top. It's okay to have a radical in the numerator, just not in the denominator. So let's practice simplifying these or rationalizing the denominator. So the first thing I'm going to do here is to kind of make it the same is I'm going to employ that rule that we just had where I was breaking up the fraction because that was the second criteria in simplifying radicals. Oh my goodness, so many words. So the problem here is that root 3 is in the bottom. So if I want to get rid of root 3 in the bottom, I could multiply the bottom by root 3. But if I do that, I have to multiply the top by root 3. Multiplying root 3 times root 3 gives me a 3. If you want, you can take that in your calculator. So take the square root of 3 and then multiply it by the square root of 3 and check to see that that's what it equals. On the top, I'd have the square root of 3, and that's okay. There's nothing wrong with having the radical in the numerator of your fraction. If I work through this page, I'll just work as I can see them. I break up the fraction, and then I'm rationalizing that denominator. I'm getting rid of the radical in the denominator. So I get a 3 down below and a root 6 up top. And I'm done. In this one, I break it apart. I rationalize my denominator. I get a 5 down below and a root 10 up top. For C, I'm going to break it apart into the 2 parts. Oops, that's a 7, not a 6. And then I rationalize the denominator by multiplying the top and bottom by whatever is in that denominator. So I'd have root 7 all over 7. For E, if I take a look at this one, I take the square root of 3x and the square root of 7, breaking it up, and then rationalizing my denominator. Last one on this page, break it up, and then rationalize the denominator. It's tempting to get cancelitis here, but you can't simplify these because you have different things going on with them. And so you're not allowed to go any further than this. In the next ones, we are going to get into a little bit of reducing. They are definitely the challenge ones. So we've got just a few more to take a look at. I'm going to break them up. I'm going to rationalize my denominator. I would have to use all three skills in simplifying here, because when I get to this point, you might figure you're done because we broke it up, we rationalized the denominator, but you should always look at whatever's under the radical sign suspiciously. That root 24 can be broken up into root 4 and root 6, that very first thing that we were doing in this chapter. Now that we've taken the perfect square factor out the front, we can take the square root of it. And you would think we were done. One more step. We've got a 2 over 8. So just as fraction math goes, we can take this one step further. My final answer for this one, just going to scroll a wee bit, would be root 6 or 1 times root 6 all over 4. One last one that's similar to this employs all three skills that we've learned in chapter 9 so far, or 9.2. Break it up, rationalize my denominator, put it back together, and then look suspiciously. Anytime you think you're done, you should look at what's under that radical sign and see if there's any perfect square factors of that number. So I could break 60 up into root 4 and root 15. All over 12. I can take the square root of that perfect square factor that I identified. And again with this one, I have to reduce in order to be done. As far as fraction math goes, I'm dividing top and bottom by 2. And so I'd be left with 1 times 15 or just, root 15 or just root 15 all over 6. So those are some challenge ones that don't involve variables. We're going to do just a couple more here to round out the questions from our textbook, and really the same approach. So I'm going to talk through them and see if we can get there. So I want to break this up because we can't have a fraction underneath. I want to rationalize my denominator. So same pattern, just more complicated. So then I would have 3y on the bottom, right? The whole act of rationalizing was get rid of that square root sign. And then on the top, I'd have the square root of 24x cubed y. Taking a look at that numerator suspiciously because it's under the radical sign, I can break it up into its perfect square component and anything that is left behind. One last step would give me my final answer, taking the square root of that perfect square factor that I identified and calling it quits. Check your coefficients to make sure there's nothing that needs to be reduced, but that should work. Oh, I forgot an x in there. Whoops, sorry about that. So there should be an x in your answer there. Okay, I'm happy with that now. All right, one more then. See if I don't mess this one up. I'm going to break it up because we can't have a fraction under the radical sign. I'm going to rationalize my denominator because I don't like having a radical down there. I'm going to hate playing this back and listening to me use those words over and over again. They're hard to keep straight. Whoops, why did I do that? It has to be the same thing top and bottom, like the same, like 5b. There we go. So then on top, I'd put this back together. I'd have the square root of 60 a cubed b. And now I can take a look at that square root of 60 a cubed b and break it up into anything that's a perfect square and anything that's left behind. So how about a 4 and an a squared? And that's going to leave me with a 15, another a and the b. This is going to be all over 5b. Last step is to take the square root of that perfect square that you've crafted out the front there. So my final answer would be 2a times 15ab on the top all over 5b. So that has it for 9.2. There's not too many questions for your text homework. And then the last chapter that we do is not in your textbook. It's a separate little unit on trigonometry. Almost there.